Hello everyone, my name is Mahyar Moghaddam from the University of Southern Denmark. I'm gonna present our work performed together with my colleagues from the University of L'Aquila. As you see the title, the work is regarding considering human behavior in designing software architecture. The work is in the context of understanding the human social and mobility behavior within an environment monitored by Internet of Things systems, and afterwards engineering and adapting the system based on those behaviors. We consider humans' quality of experience, that could be comfort, could be urban security, and so on, as an important factor in our software system design. As you see in the figure, we design a simulation environment that's able to model realistic human and system behavior. The simulation could help understanding and implementing necessary changes to improve the quality of real system. We're going to approach, our approach involves four layers as you see in here. The first layer deals with the modeling and simulation of different agents using the agent-based modeling and agent-based social simulation approach. On the agent-based model of Internet of Things systems consists of four classes of agents. The first is, of course, human agents. The second is cyber elements, then physical elements, then IoT resources, which are all parts of the environment. So here we model not only the human behavior, but also the Internet of Things systems within the agent-based modeling. We assign realistic values regarding age, gender, vision, social attachment, grouping, and so on, and run the simulations to input the IoT modeling phases. The second layer, as you see here, receives the results of agent-based simulations to generate the data required for IoT simulation. The next step models and simulates different architectural models and configurations based on the data received from the agent IoT composition. And the final step processes the IoT simulation results by considering the quality of service and quality of experience goals. We applied our approach to crowd monitoring of Uffizi galleries in Florence, Italy. We gathered data for 2 years approximately regarding human behaviors and interaction, and then fed our simulation with that. We considered two scenarios, as you see in the table. One is regarding the usual human behavior that may create congestion, and the next scenario was regarding human grouping and social attachment. We created, as you see in the picture, complex models of human behaviors that you can see in here, and provided suggestions for crowd management and actually queue management and different services that they are dealing with in Uffizi. We also provided data necessary for architectural modeling that I'm presenting here. As you see in this step, we modeled the IoT architecture of Uffizi case using CAPS modeling framework and simulated those models with CAP Carbon simulator. The CAP Carbon simulation actually considers 6 different architectural models, as you see in the first table, along with 3 configurations. And so the simulations were also according to the 2 agent-based models that I explained in the last slide. As I said, in the first table, you can see the various models, which vary based on sensors type and number of sensors. And the second table shows the configuration in normal and critical modes that, of course, impacts the data transmission frequency. Here I show the results. And here we define scenario, a specific quality of service and quality of experience goals, and assigned a trade-off metrics for decision-making purposes, actually. We use total energy consumed by the system for every 15 minutes as the parameter for measuring quality of service. And then the total count of humans gathered by the server every 15 minutes as the parameter for measuring quality of experience. In the table, you see E average, that's the average energy consumed, and H average, that's the average human captured by the sensors. The TS is also the trade-off metrics. The results show that in the first agent-based scenario that we modeled, model 3 with configuration 1 provides the highest trade-off score by giving the more preference to quality of experience within the compromising too much of the quality of service. So it is actually the preference is given to quality of experience. The second scenario says that model 6 with configuration 2 offers the highest trade-off score value. So it is different from scenario 1. And so this kind of approach could support designing the human-oriented architectures with considering both humans and system behavior in the optimal design decisions. We conclude our discussion with the fact that our approach could specify design alternatives by considering quality of experience and quality of service towards a system that provides humans and systems sustainability. In future work, we would like to investigate self-adaptation approach to adapt the architecture based on human behavior in runtime and using a data-driven approach for decision making. I would be happy to answer your potential questions.